Imagine a black hole, that cosmic vacuum of gravity, shrouded in a thick veil of gas so dense it warps light itself, turning its usual darkness into an eerie, reddish glow, a celestial beast born in the universe's infancy, when stars were just learning to shine. This isn't just any black hole, it's a relic from cosmic dawn, a time when the cosmos was a chaotic, star-strewn womb. The gas surrounding it isn't just a backdrop, it's a furnace, heating up to millions of degrees, scattering and stretching light into the visible spectrum, as if the universe itself is holding its breath. Scientists call this phenomenon gas-reddened, but what they're really witnessing is a black hole defying its own nature, glowing like an ember in the primordial dark. How did such a beast form so soon after the Big Bang? And why does its light twist and shimmer like a mirage? This is the story of a black hole that shouldn't exist, yet here it is, glowing defiantly in the dawn of time. In the earliest moments of the universe, when the cosmos was still young and teeming with primordial gas, astronomers have uncovered a phenomenon that challenges our understanding of black holes and their role in shaping the universe. At a time when the first stars and galaxies were just beginning to form around 13 billion years ago, a black hole has been discovered that is both gas-enshrouded and gas-reddened. This finding, announced in recent research, offers a glimpse into the mysterious processes that governed the cosmos during its formative years. But what does it mean for our knowledge of black holes, and how did this discovery come to light? Let's explore the story behind this remarkable find. To understand this discovery, we first need to step back to the dawn of the universe. Cosmic dawn refers to the period in the early universe when the first stars and galaxies began to take shape. This era, which occurred roughly 13 to 14 billion years ago, was a time of intense activity. The universe was still filled with a vast cloud of gas, primarily hydrogen and helium, left over from the Big Bang. As gravity pulled this gas together, it formed the first stars, which in turn gave rise to the first galaxies. These galaxies, in turn, hosted the seeds of the supermassive black holes that now reside at the centers of most large galaxies today. Now, the black hole in question is not just any black hole. It is an extremely luminous object known as a quasar, which is powered by a supermassive black hole actively accreting matter. Quasars are among the most energetic objects in the universe, emitting vast amounts of light across the electromagnetic spectrum. However, this particular quasar is unique because it is both gas-enshrouded and gas-reddened. The term gas-enshrouded suggests that the black hole is surrounded by a thick layer of gas, which may be obscuring its light. The gas-reddened part refers to the fact that the light from the black hole has been shifted to longer wavelengths, making it appear redder. This redshift is not due to the gas itself but rather the expansion of the universe, which stretches the wavelength of light over vast distances. However, the presence of gas around the black hole complicates our ability to observe it directly, as the gas can absorb or scatter light, making it harder to detect. The discovery of this black hole is significant because it provides insight into how supermassive black holes formed so quickly in the early universe. Traditionally, scientists believed that supermassive black holes grew over billions of years by gradually accreting gas and merging with other black holes. However, the existence of a quasar like this one, which is already massive and luminous at such an early time, suggests that these black holes may have formed through different mechanisms. One possibility is that they formed from the direct collapse of massive gas clouds, bypassing the slower process of star formation. Another theory is that they grew rapidly by accreting gas at an extremely high rate, fueled by the dense environments of the early universe. To detect this black hole, astronomers used advanced observational techniques and powerful telescopes. The study that led to this discovery relied on data from instruments like the James Webb Space Telescope and ground-based observatories equipped with high-resolution spectrographs. These tools allowed researchers to peer back in time to the early universe and analyze the light emitted by distant objects. By studying the light from this quasar, scientists were able to infer the presence of the black hole and its surrounding gas. The redshift of the light provided a crucial clue about the distance of the object, while the characteristics of the light helped determine the nature of the black hole and its environment. One of the most intriguing aspects of this discovery is the interplay between the black hole and its surrounding gas. The gas-enshrouded nature of the black hole suggests that it is embedded in a dense, turbulent environment. This gas may be feeding the black hole, providing the material it needs to sustain its immense luminosity. However, the same gas that fuels the black hole can also make it difficult to observe. The thick layer of gas can absorb or scatter light, making the black hole appear dimmer or even hidden from direct view. This phenomenon, known as obscuration, is a common challenge in studying distant objects, especially in the early universe where the density of gas was much higher. The gas-reddened aspect of this black hole also has implications for our understanding of the universe's expansion. The redshift of the light from this quasar is a direct consequence of the universe's expansion, which stretches the wavelength of light over time. By measuring the redshift, astronomers can determine how far away the object is and how long ago the light was emitted. In this case, the redshift indicates that the light has traveled for about 13 billion years to reach us, placing the black hole in the era of cosmic dawn. This timing is crucial because it allows scientists to study the conditions of the early universe and how they influenced the formation of the first galaxies and black holes. Another fascinating aspect of this discovery is the potential for future research. The existence of such a massive black hole so early in the universe raises questions about the mechanisms that allowed it to form so quickly. Scientists are now exploring various hypotheses to explain this phenomenon. One possibility is that the black hole formed from the direct collapse of a massive gas cloud, bypassing the typical process of star formation. This would mean that the black hole did not originate from a stellar remnant but instead formed directly from the collapse of a gas cloud under its own gravity. Another theory suggests that the black hole grew rapidly by accreting gas at an extremely high rate, fueled by the dense environments of the early universe. The implications of this discovery extend beyond just understanding black holes. It also sheds light on the evolution of galaxies and the role of supermassive black holes in shaping them. In the early universe, the interplay between gas, stars, and black holes was likely more intense than in the present day. The presence of a massive black hole at such an early time suggests that these objects played a significant role in the formation and evolution of galaxies. By studying objects like this quasar, astronomers can gain insights into how galaxies formed and how their central black holes influence their growth. Moreover, this discovery highlights the importance of advanced observational techniques in uncovering the secrets of the early universe. The ability to detect and study objects like this quasar relies on cutting-edge technology and the development of powerful telescopes capable of peering back in time. As our instruments become more sophisticated, we can expect to uncover more such objects, each providing new clues about the universe's past. These discoveries not only expand our knowledge of the cosmos but also challenge our existing theories, pushing the boundaries of what we know about the universe and its origins. In conclusion, the discovery of a gas-enshrouded and gas-reddened black hole at cosmic dawn is a significant milestone in our understanding of the early universe. It offers a unique glimpse into the processes that governed the formation of the first stars, galaxies, and supermassive black holes. By studying such objects, astronomers can piece together the story of the universe's evolution, from its chaotic beginnings to the structured cosmos we observe today. This black hole, with its enigmatic properties and distant origins, serves as a reminder of the vast mysteries that still lie beyond our current understanding, waiting to be uncovered by the next generation of scientists and explorers. The discovery of a gas-enshrouded and gas-reddened black hole at cosmic dawn represents one of the most profound breakthroughs in modern astrophysics. To understand how scientists arrived at this conclusion, we must first consider the immense challenges of observing such an ancient and distant object. Cosmic dawn, the era when the first galaxies began to form, occurred around 13 billion years ago. The light from this black hole has traveled for that entire duration to reach us, stretching into the infrared spectrum due to the universe's expansion. This redshift makes the object nearly invisible to traditional optical telescopes, requiring instruments capable of detecting faint, distant signals. The journey to confirm this black hole's existence involved decades of technological innovation, meticulous data analysis, and a collaborative effort spanning multiple observatories. Let's walk through how this discovery came to light. The first step in this process was the development of the James Webb Space Telescope, JWST, a revolutionary instrument designed to peer into the early universe. Launched in 2021, JWST's primary mirror, nearly the size of a tennis court, is optimized for infrared observations. Its advanced sensors and adaptive optics allowed scientists to capture light from objects that existed just a few 100 million years after the Big Bang. However, even with JWST's capabilities, detecting a black hole shrouded in gas required more than just powerful telescopes. It demanded a deep understanding of how light interacts with interstellar material. A key insight came from the study of active galactic nuclei, AGN, the luminous regions surrounding supermassive black holes. These objects emit vast amounts of energy as matter spirals into the black hole, forming an accretion disk. However, in the early universe, many AGN were obscured by thick clouds of gas and dust, a phenomenon known as dust obscuration. This absorption of light shifts the emitted spectrum toward longer wavelengths, making the AGN appear reddened, a signature that scientists could detect. The challenge lay in distinguishing this reddening from other cosmic phenomena, such as the natural redshift of distant objects. By combining JWST's infrared imaging with spectroscopic analysis, researchers could map the distribution of gas around the black hole and identify its unique spectral fingerprints. The process began with targeted observations of high redshift regions of the universe, where the earliest galaxies and black holes were expected to reside. Using JWST's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, scientists scanned vast swaths of the sky, searching for faint, extended sources that might indicate the presence of an obscured AGN. These observations revealed a peculiar object, a compact, luminous core surrounded by a diffuse, reddened halo. The halo structure suggested the presence of a massive amount of gas, possibly obscuring the black hole's accretion disk. But to confirm this, further analysis was needed. Spectroscopy became the critical tool in unraveling the object's nature. By splitting the light into its component wavelengths, scientists could identify the chemical signatures of gas and dust. JWST's spectrographs, such as the near-infrared spectrograph, NIRSpec, allowed researchers to measure the redshift of the object's light with unprecedented precision. This redshift, combined with the observed spectral features, indicated that the black hole was not only ancient but also surrounded by a dense, ionized gas cloud. The gas was absorbing and re-emitting light at specific wavelengths, creating a reddening effect that distorted the AGN spectrum. This absorption pattern matched theoretical models of gas-rich environments around growing supermassive black holes, providing strong evidence for the object's nature. However, confirming the presence of a black hole required more than just spectral analysis. The team needed to rule out alternative explanations, such as a massive star-forming region or a different type of obscured object. To do this, they compared their findings with data from other telescopes, including the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope. ALMA, which operates in the millimeter wavelength range, was particularly useful for detecting cold gas clouds, while Hubble's optical observations helped contextualize the object's environment. By cross-referencing these datasets, scientists could isolate the black hole's signature and eliminate confounding factors. Another critical aspect of the discovery involved modeling the black hole's behavior. Using computational simulations, researchers tested how the observed light patterns could arise from different scenarios. They found that the most plausible explanation was a supermassive black hole accreting gas at a high rate, with its emissions being heavily obscured by surrounding material. The simulations also revealed that the gas was likely heated by the black hole's intense gravitational pull, creating a luminous, reddened halo. These models not only confirmed the black hole's existence but also provided insights into its growth rate and the conditions of its environment. The timeline of this discovery unfolded over several years. Initial JWST observations in 2022 identified the candidate object, but confirming its nature required extensive follow-up. By 2023, the team had gathered enough data to publish their findings, detailing the black hole's properties and its implications for early universe astrophysics. The confirmation process highlighted the importance of patience and precision in scientific research. Each observation had to be scrutinized for potential errors, and the team had to account for the limitations of their instruments. For example, JWST's infrared sensors, while incredibly sensitive, still faced challenges in distinguishing between different types of obscured objects. Overcoming these hurdles required innovative data analysis techniques and a deep understanding of the universe's early history. This discovery also built on decades of prior research. Theoretical models predicting the existence of obscured AGN in the early universe had been around for years, but without the right tools, these predictions remained untestable. The development of JWST was a direct response to these challenges, funded by decades of scientific planning and international collaboration. The telescope's launch marked the culmination of a long effort to explore the cosmos' most distant and enigmatic regions. By combining cutting-edge technology with rigorous analysis, scientists were able to confirm the presence of a black hole that had been hidden for billions of years. The implications of this discovery are profound. It provides direct evidence that supermassive black holes were already forming and growing in the early universe, challenging existing theories about their evolution. The presence of such a massive, gas-rich environment around a black hole also suggests that these objects played a crucial role in shaping their host galaxies. By accreting gas and emitting intense radiation, they may have influenced star formation and galaxy structure in ways previously only hypothesized. This black hole, therefore, is not just a distant curiosity, it is a key piece of the puzzle in understanding the universe's earliest epochs. In the end, the journey to confirm this black hole's existence was a testament to human ingenuity and perseverance. It required the development of revolutionary technology, the collaboration of global scientific communities, and the patience to sift through vast amounts of data. Each step, from the initial observations to the final confirmation, revealed the power of modern astronomy to peer into the universe's past. As we continue to explore the cosmos, discoveries like this remind us that the universe is still full of mysteries waiting to be uncovered. In the vast expanse of the cosmos, the first stars and galaxies began to take shape during a period known as cosmic dawn, a time when the universe was still young, less than 1 billion years old. It was an era of transformation, as the primordial gas that filled the universe started to collapse under its own gravity, giving rise to the first luminous objects. Among these nascent structures, a peculiar phenomenon has emerged, a black hole shrouded in gas, its light stretched and reddened by the relentless expansion of the universe. This discovery, made possible by advanced telescopes like the James Webb Space Telescope, has profound implications for our understanding of how the universe evolved. But why is this particular black hole significant? What does its existence tell us about the forces at play in the early universe? Let's delve into the science behind this cosmic anomaly and its role in shaping the cosmos as we know it. At the heart of this discovery lies the concept of redshift, a phenomenon that has long been a cornerstone of observational astronomy. As the universe expands, the light emitted by distant objects is stretched to longer wavelengths, shifting it toward the red end of the spectrum. This effect, known as cosmological redshift, allows astronomers to measure how far away an object is and how long ago its light was emitted. In the case of this black hole, the reddening of its light indicates that it is among the most distant objects ever observed, existing when the universe was just a fraction of its current age. But redshift is more than just a measure of distance, it also provides a window into the universe's past, revealing how the fabric of spacetime has stretched over billions of years. The black hole in question is not just distant, it is also enshrouded in a dense cloud of gas, a phenomenon that has captivated astronomers for decades. When a black hole accretes matter, it generates immense energy, often outshining entire galaxies. However, in the early universe, the conditions were different. The gas surrounding these nascent black holes was likely hotter, denser, and more turbulent than in the modern cosmos. This environment would have influenced how the black hole grew and how its energy was emitted. The presence of such a gas cloud around this black hole suggests that it is in a phase of intense activity, with material spiraling inward and emitting radiation across the electromagnetic spectrum. Yet, the gas itself acts as a veil, obscuring much of the black hole's direct light and altering the way we observe it. This interplay between the black hole and its surrounding medium is a key factor in understanding its behavior and its impact on the surrounding environment. One of the most intriguing aspects of this discovery is the role of the James Webb Space Telescope in detecting such an object. Unlike its predecessors, which primarily observed in visible and ultraviolet wavelengths, the James Webb Telescope is optimized for infrared light. This capability is crucial for studying the early universe, where the light from distant objects has been stretched into the infrared range due to cosmic expansion. By capturing this infrared light, the telescope can peer through the veil of gas and dust that obscures the earliest epochs of cosmic history. The ability to detect and analyze the reddened light from this black hole represents a major breakthrough, as it allows astronomers to study objects that were previously hidden from view. This technological advancement has not only expanded our observational capabilities but also deepened our understanding of the processes that governed the universe's infancy. The significance of this black hole extends beyond its mere existence. It challenges existing models of black hole formation and growth. In the modern universe, black holes are thought to have grown through a combination of accretion and mergers, gradually accumulating mass over billions of years. However, the discovery of a massive black hole at such an early stage suggests that the mechanisms driving black hole growth may have been different in the universe's youth. This raises important questions about the conditions that allowed such rapid growth. Was the gas surrounding this black hole particularly dense, enabling it to accrete material at an accelerated rate? Did the presence of other massive objects in the vicinity facilitate mergers that contributed to its growth? These uncertainties highlight the complexity of black hole evolution and underscore the need for further research to refine our theoretical models. Moreover, the presence of this gas-enshrouded black hole has implications for the formation of the first galaxies. In the early universe, the interplay between dark matter, gas, and the energy emitted by growing black holes played a critical role in shaping the structure of the cosmos. The intense radiation and energy released by these nascent black holes could have influenced the surrounding gas, affecting how stars formed and how galaxies coalesced. This process, known as feedback, is a key mechanism in galaxy formation, as it regulates the balance between star formation and the suppression of gas cooling. By studying such objects, astronomers can gain insights into how these feedback mechanisms operated in the early universe, providing a more complete picture of the forces that shaped the cosmos. The study of gas-reddened black holes also offers a unique opportunity to explore the interplay between gravity and the expansion of the universe. In the early universe, the density of matter was much higher, and the rate of expansion was different from what it is today. These conditions would have influenced the behavior of black holes and their surrounding environments in ways that are still not fully understood. For instance, the intense gravitational pull of a growing black hole could have affected the distribution of dark matter, potentially influencing the formation of the first galaxy clusters. Additionally, the energy emitted by these objects may have played a role in reheating the intergalactic medium, a process that could have had far-reaching consequences for the evolution of the universe. As we continue to probe the mysteries of the early universe, discoveries like this gas-enshrouded black hole serve as vital pieces of the puzzle. They remind us that the cosmos is a dynamic and ever-changing entity, shaped by the interplay of fundamental forces and the intricate dance of matter and energy. Each new observation brings us closer to understanding the origins of the universe and the processes that have governed its evolution. The study of such objects is not just an academic pursuit, it is a quest to uncover the fundamental principles that underpin the structure and behavior of the cosmos. In the end, these discoveries challenge us to rethink our assumptions, refine our models, and deepen our appreciation for the vast and complex universe we inhabit. The story of a gas-enshrouded and gas-reddened black hole at cosmic dawn is not just about a single celestial object, but about the evolution of human understanding of the universe itself. For centuries, the night sky has been a canvas of mystery, and the quest to unravel its secrets has driven scientific inquiry. But it wasn't until the 20th century that we began to grasp the true scale and complexity of the cosmos. The discovery of black holes, the study of the early universe, and the development of technologies like the James Webb Space Telescope have all played pivotal roles in shaping our current understanding. Let's take a journey through time to see how these milestones led us to this moment of cosmic revelation. In the early 1900s, the foundations of modern astrophysics were being laid. Einstein's theory of general relativity, published in 1915, introduced the concept of spacetime curvature and predicted the existence of black holes, regions of space where gravity is so intense that not even light can escape. However, these ideas were largely theoretical, and it wasn't until the 1960s and 1970s that observational evidence began to emerge. The first confirmed black hole candidate, Cygnus X1, was identified in the 1970s, marking a turning point in our ability to study these enigmatic objects. Yet, even as scientists began to map the distribution of black holes across the universe, the question of how they formed in the earliest epochs remained unanswered. The early universe, a period known as cosmic dawn, presents a unique challenge. This era, which began around 13 billion years ago, marks the time when the first stars and galaxies began to form. Before this, the universe was a dark, dense expanse of neutral hydrogen, a time referred to as the cosmic dark ages. It wasn't until the first stars ignited that the universe started to reionize, setting the stage for the formation of galaxies and, eventually, the structures we observe today. However, studying this epoch has always been difficult because the light from these ancient objects is stretched by the expansion of the universe, making it appear in the infrared spectrum, a range of light that is challenging to observe with traditional telescopes. The breakthrough came with the development of space-based observatories capable of detecting infrared light. The Hubble Space Telescope, launched in 1990, was a monumental achievement, but its primary focus was on visible and ultraviolet wavelengths. It wasn't until the 2010s that the James Webb Space Telescope, JWST, was conceived as a successor to Hubble, designed specifically to peer into the infrared. JWST's advanced instruments allowed astronomers to observe the faint, distant light of the first galaxies, offering a glimpse into the universe's infancy. However, the discovery of a gas-enshrouded and gas-reddened black hole at cosmic dawn required more than just a powerful telescope. It demanded a deeper understanding of how black holes interact with their surroundings. Black holes are not isolated entities, they are often surrounded by accretion disks of gas and dust, which heat up to extreme temperatures and emit intense radiation. These accretion disks are crucial for studying black holes because they allow us to infer the presence of a black hole through their luminous signatures. However, the gas around these objects can also obscure our view, a phenomenon known as reddening. This occurs when the light from a black hole is absorbed or scattered by intervening gas, shifting its wavelength toward the red end of the spectrum. In the case of a gas-enshrouded black hole at cosmic dawn, this reddening effect is amplified by the vast distances involved, making the object appear even more distant and faint. The study of such objects has its roots in the work of radio astronomers in the mid-20th century. Pioneers like Jocelyn Bell Burnell, who discovered the first pulsar in 1967, demonstrated that radio waves could reveal hidden structures in the universe. These discoveries laid the groundwork for understanding how black holes and their environments emit radiation across the electromagnetic spectrum. By the 1980s and 1990s, X-ray observatories like the Chandra X-ray Observatory began to map the high-energy emissions from black holes, providing insights into their accretion processes. However, these observations were limited to nearby objects, and the challenge of studying black holes in the early universe remained. The key to unlocking the secrets of cosmic dawn lies in the combination of advanced observational techniques and theoretical models. The discovery of distant quasars, luminous active galactic nuclei powered by supermassive black holes, provided early evidence that black holes existed in the early universe. These quasars, which emit vast amounts of energy, were detected using optical and radio telescopes, but their study was hampered by the difficulty of distinguishing between the light from the black hole itself and the surrounding gas. It wasn't until the advent of infrared astronomy that scientists could begin to unravel these complexities. The James Webb Space Telescope, launched in 2021, has revolutionized our ability to study the early universe. Its infrared capabilities allow astronomers to peer through the cosmic fog, capturing light that has traveled billions of years to reach us. This has enabled the detection of some of the first galaxies, which are often shrouded in gas and dust. However, the discovery of a gas-enshrouded and gas-reddened black hole at cosmic dawn represents a new frontier. Such an object would not only be a rare find but also a critical piece of the puzzle in understanding how black holes formed and evolved in the earliest epochs of the universe. The journey to this discovery has been shaped by decades of scientific progress. From the theoretical predictions of Einstein to the observational breakthroughs of Hubble and JWST, each step has built upon the last. The study of black holes has evolved from a niche area of astrophysics to a central theme in our understanding of the cosmos. As we continue to refine our tools and techniques, we are uncovering new insights into the nature of these enigmatic objects and their role in the universe's history. The gas-enshrouded and gas-reddened black hole at cosmic dawn is not just a scientific curiosity, it is a testament to the enduring human drive to explore the unknown and to seek answers to the universe's most profound questions. A gas-enshrouded and gas-reddened black hole at cosmic dawn. This part of our deep dive into a gas-enshrouded and gas-reddened black hole at cosmic dawn focuses on explore the open questions, scientific debate, and things that remain genuinely unresolved or mysterious. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. As we peer deeper into the cosmos, the next chapter in our exploration of gas-enshrouded and gas-reddened black holes at cosmic dawn hinges on the development of cutting-edge observatories and instruments. These tools, designed to push the boundaries of our observational capabilities, will not only confirm the existence of such enigmatic objects but also challenge our current understanding of the early universe. The James Webb Space Telescope, already a cornerstone of modern astronomy, will play a pivotal role in this endeavor. Its advanced infrared sensors are uniquely suited to detect the faint, redshifted light from distant objects, making it an ideal instrument for studying these elusive black holes. However, the quest for knowledge extends beyond the capabilities of existing telescopes, and several upcoming missions promise to revolutionize our ability to observe and analyze these cosmic phenomena. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will complement JWST's efforts by conducting wide-field surveys that could uncover more of these gas-reddened black holes. With its large mirror and advanced technology, the Roman telescope will be able to detect subtle variations in light that might indicate the presence of such objects, even in the densest and most obscured regions of the early universe. In parallel, ground-based observatories like the Square Kilometre Array, SKA, are being developed to harness the power of radio waves. The SKA, with its unprecedented sensitivity, will be capable of detecting the faint radio emissions from accretion disks around black holes, providing crucial insights into their behavior and the surrounding gas dynamics. These radio observations could reveal how the gas interacts with the black hole's intense gravitational field, shedding light on the processes that govern star formation and galaxy evolution in the early universe. Furthermore, the upcoming Large Ultraviolet Optical Infrared Surveyor, LUVOIR, and the Habitable Worlds Observatory, HWO, represent the next generation of space-based telescopes. These missions, still in the planning stages, are designed to achieve even greater resolution and sensitivity, allowing scientists to probe the atmospheres of exoplanets and study the environments around distant black holes in unprecedented detail. LUVOIR, for instance, could potentially capture high-resolution images of the accretion disks around these gas-reddened black holes, revealing intricate structures that might have been previously invisible. Similarly, HWO's advanced spectroscopic capabilities could help astronomers analyze the chemical composition of the gas surrounding these objects, providing clues about the conditions in the early universe. The development of these instruments is not without challenges, however. The sheer scale of these projects requires international collaboration and significant investment, as well as overcoming technical hurdles that have long plagued space-based observatories. For example, the SKA's massive array of radio antennas must be constructed in remote locations to minimize interference from Earth's electromagnetic noise, while the LUVOIR's large mirror necessitates innovative engineering solutions to ensure its stability and precision. Despite these challenges, the potential rewards are immense. By combining data from multiple observatories, scientists will be able to build a more comprehensive picture of these gas-reddened black holes and their role in the cosmos. The upcoming missions will also enable researchers to test and refine existing theories about black hole formation and evolution. For instance, if observations reveal that these black holes are forming in ways that contradict current models, it could prompt a re-evaluation of our understanding of how supermassive black holes grow in the early universe. Such findings might even challenge the prevailing theories about the role of dark matter and dark energy in shaping the cosmos. Moreover, these missions could uncover new phenomena that were previously beyond our reach. The gas-enshrouded nature of these black holes suggests that they are embedded in dense, dusty environments, which could affect how we interpret their light. By studying these environments in greater detail, astronomers might gain insights into the processes that govern the formation of galaxies and the distribution of matter in the early universe. The upcoming instruments will also play a crucial role in addressing some of the most pressing questions in astrophysics. For example, how did the first galaxies form? What role did black holes play in their evolution? And how did the universe transition from a state of darkness to one illuminated by stars and galaxies? By observing these gas-reddened black holes, scientists can piece together the timeline of cosmic events, providing answers to these fundamental questions. However, the journey to uncover these secrets is not without its uncertainties. The early universe was a chaotic and dynamic environment, and the conditions that gave rise to these black holes may be unlike anything we have observed in more recent cosmic history. This means that our current models and assumptions may need to be revised as new data becomes available. The upcoming missions will therefore serve not only to confirm existing theories but also to challenge them, driving the field of astrophysics into new and uncharted territories. In addition to these observational efforts, theoretical advancements will also play a vital role in interpreting the data collected by these instruments. As we gather more information about these gas-reddened black holes, physicists and astronomers will need to develop new models that account for the complex interactions between gas, radiation, and gravity in the early universe. These models will help us understand not only the behavior of individual black holes but also their collective impact on the structure and evolution of the cosmos. The interplay between observation and theory will be a key driver of progress in this field, ensuring that each new discovery leads to further questions and deeper insights. As we look to the future, it is clear that the study of gas-enshrouded and gas-reddened black holes at cosmic dawn is just beginning. The upcoming missions and instruments will provide the tools necessary to explore these enigmatic objects in ways that were previously unimaginable. By combining the power of cutting-edge technology with the ingenuity of human curiosity, we are poised to unlock some of the universe's most profound mysteries. The journey ahead is as exciting as it is challenging, and the discoveries that await us promise to reshape our understanding of the cosmos in ways that will inspire generations of scientists and stargazers alike. So, what did we uncover in this deep dive? Let me break it down. First, we discovered that black holes at cosmic dawn, those earliest moments of the universe, aren't just silent monsters devouring matter. They're surrounded by thick, glowing gas, which scatters and reddens their light. This gas isn't just a passive veil, it's a dynamic environment, shaping how we see these ancient beasts. Second, this reddening effect is a clue. It tells us the gas is ionized, likely by intense radiation from the black hole itself. That creates a feedback loop. The gas heats up, emits light, and maybe even slows down the black hole's growth. It's like a cosmic dance between consumption and emission. Third, this observation bridges a gap in our understanding. For years, scientists have debated how supermassive black holes formed so quickly after the Big Bang. This gas-enshrouded black hole at cosmic dawn offers a possible answer. These early black holes might have grown rapidly by accreting gas in dense, turbulent environments. But here's the kicker: the gas isn't just slowing them down. It's also hiding them. The reddening makes them harder to detect, which explains why we've only recently started spotting these ancient objects. This discovery isn't just about one black hole, it's about rewriting the story of how black holes and galaxies evolved together. The gas isn't just a backdrop, it's a key player, influencing everything from star formation to the structure of the universe itself. And yet, there's still so much to learn. How common are these gas-enshrouded black holes? What role does the gas play in their growth? Are there other factors we're missing? These questions aren't just academic, they're vital to understanding the cosmos. So, if you've enjoyed this deep dive, hit that subscribe button to stay tuned for more explorations of the universe's biggest mysteries. And if you've got your own theories or questions about gas-reddened black holes or cosmic dawn, drop them in the comments. Let's keep unraveling the universe, one discovery at a time.